So let's continue with this review. We are now ready for problem 24. So in the last video, we did a problem with this thing called a difference quotient. And you notice now what they've done is they've taken the difference quotient and taken the limit as h approaches 0. And you notice this is actually the definition of the derivative, right? This symbol, f prime of x, that's a symbol for the first derivative. So the difference quotient, you take the limit as h approaches 0, and you have the first derivative. So what they want us to do here, which is sort of interesting because when I teach this class, I tell my students, this is the painful, hard, long way to calculate the first derivative. And I say, pretty quick, you're going to learn shortcuts so that you will never have to do it the long and painful way ever again. But I guess in the world of math, they want students to suffer through doing it the hard way before they learn the easy way. So actually, we'll go ahead and do this problem the long way. Although even on the test, honestly, if you were given this problem on the test, if you want to find the correct answer, it seems sort of crazy to do it the long way when you know another way to do it, and you can do it in maybe 20 seconds as opposed to 5 minutes. So let's go ahead. Maybe I'll write this problem down and I'll do it, and I'll sort of show you what I mean. So the function we're given is f of x equals 7x squared. It's interesting. The other problem we did, the function was also x squared. And for the actual problem, they want the first derivative when x is 6. So here's the problem. We're given a function. What they really want to do is to determine the first derivative and then plug in x equals 6 into the first derivative and see what that equals. Of course, the first step is, once you're given a function, you need to find the first derivative. Now I'm going to do this one the long way and then the short way, and you'll see obviously you get the same answer, and then you'll see why no one ever does it the long way, because it's not necessary. So the long way, this original definition of the first derivative is the limit problem. The limit as h approaches 0 of this difference function. And once again, big picture, you know what I told you last time the difference function is? It's the slope. You know what the first derivative really is determining? The slope. That's really what the first derivative is. The first derivative is the slope. So if I'm going to do it the long way, I'm going to skip a few steps. First of all, f of x plus h is going to be 7x squared minus 14xh minus 7h squared. That's f of x plus h. So that's taking my function, and every place I have x, I plug in x plus h. And when you multiply it out and do all the work, well, let me just show you real quick over here. if f of x is 7x squared, f of x plus h is 7 times x plus h squared. So once again, you multiply out the x plus h squared, then you multiply it by 7, and you should get this. Then we have minus f of x, which is 7x squared, all that over h. So we're taking the limit of this whole thing. Now we should simplify this, and you notice the 7x squared minus 7x squared cancels out. So I end up with, oh, this should not be, I don't know why I put negative here. Sorry about that. These are all plus. Don't know where that came from. So these are all plus, but so the 7x squared minus 7x squared cancels out. So I'm left with 14xh plus 7h squared over h. Now you notice I can cancel out some h's, or at least one h. So you have 14x plus 7h. So the first derivative is a limit as h approaches 0 of 14x plus 7h. Now we know how to take limits, right? You plug in the number for that variable and see what happens. If I plug in 0 for h, I end up with 14x. And that is, in fact, the first derivative. Now, what's interesting, since you're doing a review now, you've already learned that if you're given 7x squared and you're asked to find the derivative, you just bring the exponent down front. 2 times 7 is 14x, and you subtract 1, you get 14x. It actually takes maybe 5 seconds to do this derivative using what I call the shortcut, as opposed to the original definition. And that's why no one ever does this. Why would I take 5 or 10 minutes to do it this way when, if I'm given this function, I can within 5 seconds say the first derivative of this is 14x. So it does seem sort of crazy. So anyways, for this problem, now they're saying, what's the first derivative when x is 6? So you plug in 6 for x. 60 looks like 84 should be the answer. And what that's really saying is, it's saying, here's a function. If you go to that function where x is 6 and you draw your tangent line at that point, and you look at the function of that tangent line, it's going to be 84, which is really the slope of this function at that point. That's all we're really doing here. Let's go back to the problem. Hopefully when I plug in 84, it will be correct. So like I said, it's interesting how in the world of calculus, they like to make you suffer for a bit and do some of these derivatives the long way, and then they show you how to do it a more efficient and quick way. All right. So now we talk about something different when functions are what they call differentiable. Now, when you're looking at a graph, there's really, so here's a function. It's got sort of a curve here, and then a point, and then a big curve up at the top. There's like a hole there, it jumps down here, and then there's a hole here, it jumps up here. So this is a really, lots of gaps and holes and corners, all kinds of crazy things. And what the question is here is, they're saying List the points in the graph from 0 to 8 of which the function is not differentiable. There's two, when you look at a graph, there's two things you have to look for where a graph is not differentiable. The first one is where there are any gaps or breaks or holes in the graph, where the graph is not continuous, right? We talked about continuity a while ago. But continuity is not enough, because in this graph, this little corner here is, the graph is continuous here. The second thing you have to look for are any corners. If you have any sharp corners, those are the places where it's not differentiable, which that means you can't take the first derivative. You can't have the first derivative. So if I look at this one, I start here. What I'm really saying is, every place along here, could I figure out the first derivative? Is it differentiable? Yes, it is, because I'm looking for gaps or breaks or corners. I get to here, when x is 2, I've got a corner. When x is 2, I cannot calculate the derivative when x is 2. However, when I keep going along here, I'm okay now. I can take the derivative of all this stuff, but when I get up to here, when x is 4, I've got this gap or a break. I cannot take the derivative where there's a gap or a break. So I cannot take the derivative when x is 4. However, I'm okay as I keep going on, but then I get to x equals 6. I got another break and jump, and I cannot take the derivative. So if I'm looking between x is 0 and x is 8, at what points is it not differentiable, or can I not take the first derivative? Well, I've got a corner here at x equals 2. I got a gap at x equals 4 and a gap at x equals 6. So there's 3 values of x where I cannot take the derivative. So here I should put in 2. I think you just separate the values of x with commas. Whoops. All right, so that's not too hard to understand. Hopefully you understand about when functions are differentiable. All right, 28. Or actually, whoops, 26. All right, this one says list the points. Okay, same thing, differentiable. Let's expand it. Here, the values of x, they just call x0, x1, x2, x3. It's a bunch of, looks like 6 different points here. And they want us to know, they want to ask us, which of these points is it not differentiable? Can I not take the first derivative? Well, I'm looking for, once again, gaps and corners, or where the graph doesn't exist. X of 0 is perfectly fine here. Look at x of 1. There's not even a graph there. Obviously, I can't take the derivative of something that doesn't exist. So x is 1, it's not differentiable. Look at x of 2. I got a little gap or a break here. So x of 2, it's not. X of 3 is a corner, so it's not. X of 4, another gap, it's not. X of 5 is okay. So really, 1, 2, 3, 4. x1, x2, x3, x4, it's not differentiable. x0, x5, we're okay. So 3, it's not differentiable. 2, it's not. 1, it's not. 4, it's not. Only 0 and 5. Okay. Now, draw a graph that is continuous but not differentiable. So remember, when a graph is continuous, that means you can trace out the graph without ever lifting your pen off the page. But differentiable means, not differential means we got a corner or a gap. So I'm going to find a graph that's continuous so I can draw the whole graph without lifting my pen off the page. But at the same time, there's going to be some place in the graph where I cannot take the derivative. So if I look at A, first of all, it's not continuous because look at, there's a gap here. So this is not continuous. So this problem, two things have to be true. It has to be continuous, but then not differentiable. This one's not continuous. How about this one? Is it continuous? The whole thing is connected. I could draw out this whole graph. So it is continuous. Now I'm saying, how about, is there any place where I cannot take the first derivative? I've got a corner here. I cannot take the derivative here. So this graph is continuous, but not differentiable. My guess is this is probably the answer. But just to make sure, let's go look at the rest of them. If I look at C, is it continuous? Yes, it is continuous. Is there any place on here where I cannot take the first derivative? Are there any corners or gaps? No. I can take the derivative every place. So that's not the answer. And just for fun, we'll look at the last one. Is it continuous? Obviously it's not. There's a gap there. So the only one that fits the criteria is B, and that should be the correct answer. So now we get the idea of when you have these graphs and curves and functions, the whole principle of the tangent lines, right? Where a tangent line is a line that comes right next to the graph. It just touches the graph at one point. It does not cross the graph, but just touches it at one point, and those are called tangent lines. So here they're saying, here's a curve. They've drawn in a bunch of these lines, and they're saying, which one of these are tangent lines? Well, this first line, it does only touch the graph at one point, but it crosses the graph, so that's not a tangent line. L2, you can see how it touches the graph at one point, but does not cross the graph, so that's a tangent line. L3 is a tangent line. L4 is a tangent line. L5, it crosses a graph. L5 is not. L6 is. So it looks like 2, 3, 4, 6 are tangent lines. 2, 3, 4, 6. So 2, 3, 4, 6. Those are the tangent lines. So once again, tangent lines, pretty easy to understand. Oh, another question. Why do the lines selected above appear to be tangent lines, and why are they not? So here's like a definition of it. So let's see which one it is. Each tangent line is perpendicular to the graph. That's not true. The slope of each tangent line is positive. That's not true. The slope of each tangent line is equal to the slope of the graph at the point intersection between the graph and respective tangent line. The other lines are not parallel. I think it's C. All right. So now we're going to do some derivatives, but we're going to do it the short, quick, and clever way. Matter of fact, we can pretty much do this in our head, right? First derivative using the power rule, because this is like a power function, which means you've got your variable raised to an exponent, a number. What do? You bring the exponent down front, and then you subtract 1 from the exponent. So 3x. Now let me tell you something. Normally, if you're using MyMathLab, you have to go down here and click on this little superscript tool to get your exponent. But there actually is a shortcut that I use all the time. On your keyboard, there's what's called like the, a lot of times it's called a caret. It's like an up arrow. Like on my keyboard, it's the right above the number 6. And a lot of times, if you want to give an exponent, you type in a caret like this, And look what it does. Automatically, MyMathLab knows when you type in that caret symbol, that up arrow symbol, it knows that the next thing you're going to type is going to be the exponent. So instead of having to go down here and click on this, I could just type 3x, up arrow, and then my exponent, and then I'm done. So it's just quicker in terms of typing in answers. So that one was do anything except just type it in pretty much. This one's also pretty straightforward. Now here's, of course, there's two different ways to write out derivatives. One way is f prime of x. You have the little f and the little hash at the top and then x. But this other notation is, especially if you're given your original equation is y equals 9x, and of course, hopefully by now you realize that y and f of x are interchangeable. Sometimes you can write your equation y equals 9x. Other times you can write f of x equals 9x. Really means the same thing. But a lot of times if they write out, if you're given an equation and it's y equals 9x, then the derivative, they will write it this way, dy dx. So dy dx means the derivative of this. So what's the derivative of 9x? Hopefully you realize if you have a variable with no exponent, actually you can think of it as a 1 here. If you bring the 1 down front and then you subtract 1, you have x to the 0. The rule in math is what happens when you have an exponent of 0? The whole thing becomes 1. Usually, when you start doing calculus and derivatives, all you tell yourself is, if I have a variable by itself with no exponents, when I take the derivative is just 1. So you have 9 times 1. So the derivative is just 9. I think you hopefully all know that by now. What's a derivative? When you just have a constant, when there's no variable at all. Derivative of this. It's interesting. If you think about this as a function or a graph, if you were to look at the graph of y equals -12, do you know what the graph of y equals -12 looks like? It's actually a horizontal line that goes through y equals -12. And what are we doing when we take the derivative? The derivative is the slope of the line. And what's the slope of a horizontal line? Slope of a horizontal line is 0. And that's why anytime you take the derivative of a number, of a constant, derivative is always going to be 0. All right, not too hard. This one I think we can probably also do in our head. Y equals 7x to the 7th. We're asked to take the first derivative. So what do? You take the exponent 7, you bring it down front. So you have 7 times 7, which is 49. And then, of course, you've got your x, and then you subtract 1 from the original exponent. So I'm going to do my little caret and put in 6 here. And then I do my arrow right to get my cursor back here. And hit enter. Not too difficult. All right. I'm going to do also this one. I'm not going to do it on paper because this one's pretty straightforward. Here we have 4 terms. We want to take the derivative of this whole equation. But the nice thing is when you have separate terms, when you take the derivative, you can just take the derivative of each term by itself. In other words, I'm going to take the derivative of 4x cubed. The 3 comes down front, which gives you a 12. Then you have x. You subtract 1 from the 3. And you have 2. So the derivative of 4x cubed is 12x squared. Now I go here. Now the minus sign stays there. And now I bring the 2 down front, so I'd have 10x. And what's my exponent going to be here? Subtract 1 from 2, I get 1, so it's just 10x. And then now what's the derivative of 8x? Well, you know, when you have a variable by itself, the derivative of x is just going to be 1, so this is 8. And what's the derivative of a constant? It's 0. So I think I'm done. So the derivative of this expression is this right here. All right, not too hard. All right, now it gets a little trickier. So this one I'm going to have to probably do on paper. What happens is, let me write this down, then we can talk about it. So the original equation is y equals 100 over x to the 4th. So this is number 34. And they're saying y dx equals what? In other words, I want us to find the first derivative. Let's take a look at this and talk about it. So what happens is, one of the first rules we learn when we learn how to take derivatives is called the power rule. The power rule is when you have a variable with an exponent where the exponent's a number. Number could be a fraction, decimal, a number, positive, negative, doesn't matter. It's just going to be a number. And we know how to take the derivative of this. You bring the n down and you subtract 1. So this power rule applies for this situation. Now I look at my problem. I have 100 over x to the 4th. As this equation is currently written, I cannot use the power rule because the power rule doesn't apply when you have your variable in the bottom of a fraction. The power rule applies when it's just a term like this by itself. So a lot of times what you do in this case, what I'm going to do is I'm going to try and rewrite this equation so that it fits this form so that I can apply the power rule. Now, hopefully, you remember some of your exponent rules and you know, here's what I can do. I'm going to go and do it, and then hopefully you remember how this works. 100 over x to the 4th is the same thing and can be rewritten as 100 times x to the minus 4. Remember the rule about negative exponents? If you're given a negative exponent and you want to make it a positive exponent, what do? You move it to the bottom. So if I was given 100x to the minus 4th and I wanted to make it a positive exponent, it would be 100 over x to the 4th. So these are the same. But the good thing is when I write it like this, I'm in the form of the power rule. I can now apply the power rule to this equation, and therefore I'm able to take the first derivative. The 100 is a constant, it just tags along. So since this is in the form of the power rule, the minus 4 comes down front. You have your x, and then you subtract 1. So what's minus 4 minus 1? It's actually minus 5. Now we should clean this up some because 100 times minus 4 is minus 400. And normally in the world of math, they normally don't like you to leave answers with a negative exponent. So normally we switch this back to a positive exponent and the answer should become negative 400 over x to the 5th. So if I go back and type that in, hopefully it's going to be correct. Negative 400. Whoops. This needs to be a fraction. So you can type this key down here, but also sometimes in my math lab, if you just type /, once again, it by default gives you a fraction. And now x caret to the 5th. All right. So it's not too bad. Here's another case. Y equals the 5th root of 3x. The way this is written, it's not in the form that I can use the power rule. The power rule says you have to have your variable and it has to be raised to some kind of number exponent. I don't have that here. So again, I'm going to do the same thing I just did. I'm going to do a little conversion and try and rewrite that so it fits the power rule. So let me write it here, and then I will show you what we're going to do. Here's problem 35. Once again, what's the power rule? The power rule says I have the variable raised to an exponent. I don't have that here. However, we have these things called rational exponents. And rational exponents and radicals are flip sides of the same coin. We can rewrite them back and forth. Let me show you. Although the first thing I'm going to do is, because I've got this variable here, you can, when you have a radical and the stuff inside is multiplied, you can split it up into two separate radicals. You're going to see why in a minute. I do this. So this here is just like a constant. It's a number. I don't know if you wanted to find out the decimal, you'd have to go grab a calculator and figure it out, but I don't really care. I'll leave it like that. What I really care about now is this right here. I want to take the derivative of this 5th root of x, but I can't really apply the power rule. However, hopefully you guys all remember you can always convert a radical into a rational exponent. Let me just write it here. The 5th root of x is the same thing as x to the 1/5. Hopefully a quick review. Here's a rational exponent. Say you want to make that into a radical. Remember the rule. The number in the bottom becomes the root. The number in the top becomes the exponent inside. And if you go the other way around, what I just did is we had the 5th root of x. If I want to make that into a rational exponent, I'm going to have a fraction here. 5 goes on the bottom. What's my exponent for my x? It's just a 1. So the 5th root of x is the same as x to the 1/5. Now, if I want to take the derivative of this, this is just a constant. It just tags along. It's sort of, whoops, it's sort of ugly, but it just tags along. And now I can apply the power rule to this. So you have the 1/5 comes down front, x, 1/5 minus 1. I remember how to do fractions, right? 1/5 minus 1. If you want to do it mathematically, you got to have a common denominator. Looks like negative 4/5. So x to the negative 4/5. So this is really messy looking, but basically, sometimes with MyMathLab, you never know quite how they want. This is like a fifth root. Make sure it's clear. You never quite know how they want you to enter it. I'm going to take this x to the negative 4/5 and bring it to the bottom. Let me take a guess that maybe MyMathLab I wonder if it would like this. I could, of course, change these to radicals. I'm not quite sure what MyMathLab wants. Let me just type it in and see. So let me do a fraction. This is sort of messy, so let me go ahead and now I'm going to go 3. I'm going to use this exponent tool since this is going to get messy. For the 1/5, and then 5x into the 4/5. I wonder if they'll like that. Wow, I was happy with it. That's nice. All right. Let me go ahead and write this one out. So it's two terms here. Y equals x over 8 minus 8 over x. This is number 36. Y equals x over 8 minus 8 over x. And of course, we're trying to calculate the first derivative. So we have two terms. I'm wanting to use the power rule for each of these terms to make it very clear. X over 8, I can rewrite as 1/8 times x. That makes it very clear. So the power rule will apply here. But here, I've got this x in the denominator. I cannot use the power rule. However, I realize that I can move the variable to the top by making the exponent -1. So now both terms fit the power rule. So I can take the derivative. Power rule on this first term, just 1/8. Power rule for this second term, the -1 comes down front, and you subtract 1 from the exponent, so you get -2. So you have 1/8. You notice this subtract and this -1. Two negatives make a positive. And if I want to get rid of this negative exponent, I stick it in the bottom. So this becomes 1/8 plus 8 over x squared. Let's see how that works. So 1/8 plus 8 over x squared. All right, so far so good. Here, number 37, they give you a function, and now they're saying find the first derivative when x equals 2. So it's really a two-step problem. First step is you find the first derivative of the function, and then you set x equal to 2 inside your first derivative. Now, I could probably do that in my head, but just to make it clear for all of you, I will do it here on my paper. So f of x equals 2x squared minus 4x plus 8. And they're asking for the first derivative when x equals 2. Here's the problem for 37. First step is find the first derivative. 3 terms, I can apply the power rule to all these. Pretty straightforward. 4x minus 4, derivative of 8 is just 0. So that's the first derivative. Now I'm going to go in and determine what the first derivative is when x is set equal to 2, right? So you plug in 2 for x, 8 minus 4. Looks like the answer should be 4. All right. I'm going to stop here in a minute. Let me see. All right, this is the same kind of problem. The notation's different. So here they give an equation with y equals 7x plus 2 over x squared. And they say find dy dx at x equals 1. That's another way of saying go take the first derivative and then evaluate the first derivative when x is 1. So let's go ahead and do this one. This one shouldn't be too bad. This is number 38. So y equals 7x plus 2 over x squared. You'll see how I'm going to write this in a minute, how I like to write it. So here's the original equation, y equals 7x plus 2 over x squared. And then it says dy dx. You know, I like to write it here. I put this line here, and then down here I say x equals 1. So basically I'm saying take the first derivative and evaluate it when x is equal to 1. And that's what I'm trying to figure out. Now, first thing I do is I realize this first term is fine for using the power rule. The second term is not really in a form I can use the power rule. However, I can pretty easily fix that and change this to 2 times x to the minus 2. Now I can take the first derivative, 7 plus 2, minus 2 comes down front. Subtract 1 from your exponent. If I try and simplify this sum, 2 times negative 2 is negative 4, so minus 4. Now, what I want to do is I want to take that first derivative and evaluate it when x is 1. So I take this first derivative and plug in 1 for x, which is 7 minus 4. Looks like the answer, if I didn't make any mistakes, is 3. All right, good. All right, now's a good place to take a break for the next video, because now we're talking about the equation of the tangent line at the point, which we will explain how that works. So we're going to stop now and start the next video.